Hello friends, welcome to my YouTube channel Aviator Updates. This is Rakesh Negi and today I'm going to discuss about ISA, that is International Standard Atmosphere. So basically, to start with, first of all, we should know that the Earth is covered by a gaseous envelope which is called as the atmosphere. Now, this atmosphere does not have the same characteristics across wide range of its altitudes or elevations throughout the globe. So, to establish a common reference for measuring pressure, temperature, etc., it is very important to consider an average set of conditions called as International Standard Atmosphere or ISA. This ISA has its own atmospheric model. The International Standard Atmosphere model is published by International Organization for Standardization, and we should know that ICAO also publishes its own standard atmospheric model called as the ICAO Standard Atmosphere, and it is same as the ISA which we discussed just now. ICAO also publishes its own standard atmosphere model, and it's named as ICAO Standard Atmosphere, and it was published in 1993 and published in a document number 7488 CD. Note that all the aviation standards and flying rules are based on the International Standard Atmosphere. For example, one of the pressure instrument named airspeed indicator is calibrated based on the assumption that the instrument is operated at sea level ISA, that is International Standard Atmosphere, where air density is 1.225 kilogram per meter cube, air pressure is 1013.25 hectopascal or 29.921 inch mercury, and standard temperature is 15 degrees Celsius or 59 degree Fahrenheit. Note that at sea level the ISA temperature is 15 degrees Celsius, the standard pressure is 1013.25 hectopascal or 29.921 inch mercury, and standard air density is 1.225 kilogram per meter cube. So I hope you are clear with what is ISA as of now. So now, as you are clear with the International Standard Atmosphere, we will be discussing with regards to parameters like temperature and pressure. So temperature is called as the ISA temperature. Let's first discuss about the ISA temperature. So if we talk about temperature, friends, we know well with increasing altitude the temperature reduces. Why is the Earth's temperature higher at lower altitude and lower at higher altitude? The reason is because of the Earth's radiation. At lower altitude the temperature is high, and as we keep on gaining altitude, as we go high and high, the radiation of the Earth, its effect is decreasing. Hence, at higher altitudes, with increasing altitude the temperature reduces. Okay, now as you are clear with the temperature and altitude relationship, that is, relation is inverse. That means altitude is inversely proportional to temperature. Now note that in ISA conditions, for every 1000 feet increment there is a fall in temperature of 1.98 degrees Celsius. Okay, and this is called as lapse rate. So what is lapse rate? Lapse rate is fall in temperature with increasing altitude. And how much fall? 1.98 degree per 1000 feet. Approximately you can consider 1.98 degrees Celsius as 2 degrees Celsius. Okay, so I hope you are clear with what is lapse rate. So I hope you are clear with the standard temperature at sea level, that is 15 degrees Celsius. This is also called as the international reference at sea level. So the international reference at sea level is 15 degrees Celsius. So with increasing altitude the temperature reduces, and it reduces at a rate of 2 degree per 1000 feet approx temperature value I have taken, which I have said just now. Next point to note is at 36,090 feet, it is actually 36,089 feet, but approximately we are considering it as 36,090 feet. At 36,090 feet the temperature is constant, that is the temperature at 36,000 feet is minus 56.5 degrees Celsius, and thereafter it is constant. Okay, next, after 36,000 feet, when the temperature is constant, there comes a certain layer beyond which the temperature again starts increasing. I mean to say, with increasing altitude there the temperature will be increasing, and this is called as temperature inversion, which is the opposite of lapse rate. So what was happening in lapse rate? Temperature was reducing because of increasing altitude, But in case of temperature inversion, after a certain layer, after the 36,000 feet higher layers, the temperature starts increasing with increasing altitude, and that thing is called as temperature inversion. Okay, let's come back to our topic. Now I'm going to show you what is ISA temperature modeling. Okay, so I'll explain it in terms of graph. Suppose this is the x-axis. Okay, in this x-axis, suppose I have taken temperature. Suppose here is 20, then 40, then 60. Note that all temperatures are in degrees Celsius, so 20 degrees Celsius. So all these are in degrees Celsius. Okay, and this is the temperature. So this is increasing. So I'll just put a plus sign over here because I'm going to show the negative scale as well. Suppose this side is minus 20, this is minus 40, and this is minus 60. So all in degrees Celsius as mentioned. So this is temperature. This side is decreasing. Okay, and in the y-axis I am taking altitude. Suppose this is 5,000 feet, this is 10,000 feet, this is 15, then 20, 25, then 30, and then 35, and then 40. So suppose these are the altitudes, okay, in the y-axis. So now let's study how the temperature changes with respect to altitude in this model. Okay, so as discussed, I have told you that the temperature decreases with increasing altitude. So how does it decrease? It decreases at a rate of 1.98 degrees Celsius per 1,000 feet. Okay, and at 36,090 feet, which is here. So here I am marking as 36,090 feet. 36,090 feet. Okay, so here I'll just extend. So friends, with increasing altitude, the temperature decreases. In this ISA model, I'm going to show you how. So we know well the international reference for temperature at sea level is how much? 15 degrees Celsius. So I'll mark here 15 degrees Celsius. Okay, that is plus 15 degrees Celsius. Suppose this is here plus 15. So from here the temperature starts reducing with the increasing height. Here in this axis the height is increasing. Okay, so temperature starts reducing. Minus 56.5 degrees Celsius. So at this altitude, that is 36,050 feet, here onwards the temperature will be constant. And what will be the value? Minus 56.5 degrees Celsius. So this is about the temperature modeling. So what did you learn in this temperature modeling? You have learned that with increasing altitude the temperature decreases at a rate of 1.98 approx 2 degree per 1,000 feet, and on reaching 36,090 feet the temperature remains constant. Okay, and this constant value is also maintained up to a certain level, and after that level or layer, okay, after that layer the temperature starts increasing again. That is an extra knowledge. The temperature starts increasing again beyond that layer, which is upward than this, and when it starts increasing it is called as temperature inversion. Okay, so I hope you are clear with the temperature modeling. So points to be noted from this are few points. First point, the international reference temperature at sea level is plus 15 degrees Celsius. Second thing to note here is the lapse rate or the reduction in temperature per 1,000 feet is 1.98 degrees Celsius per 1,000 feet. And the other point to note here is from 36,090 feet, okay, starts tropopause. Okay, so it is a tropopause where the temperature remains constant. So from here onwards the temperature is constant. Beyond certain layers above tropopause the temperature will start increasing again, and this is called temperature inversion. Okay, so note that at mean sea level ISA temperature is plus 15 degree Celsius. Next case, above mean sea level but below tropopause. But below tropopause, that is 36,090 feet. So in this case, the ISA temperature will be plus 15 degrees Celsius minus altitude divided by 1000, and this multiplied by the lapse rate, which is 2. Okay, 2 is the lapse rate. So this is the second case and this is the first case. So these 2 points you have to remember. Okay, so in first case we are having at mean sea level the ISA temperature is plus 15, above mean sea level but below tropopause, that is 36,090 feet, we are having ISA temperature as 15 degrees Celsius minus, that means ISA temperature minus lapse rate into altitude upon 1000. So these are the points which you should keep in mind for calculating the ISA temperature. Okay, let's take an example how to calculate the ISA temperature. Suppose you want to calculate ISA temperature at 30,000 feet. Okay, so how do you calculate? I'll just give you a thumb rule. So let's do one calculation, how to find ISA temperature at a certain altitude. Let the altitude be 30,000 feet. Now at this altitude I want to calculate ISA temperature. What you do is, there is a small thumb rule, double the altitude and subtract 15 and then put a minus sign. That will be the ISA temperature at 30,000 feet. So what I said, double the altitude. So this 30, you just take this initial 2 values, you double it. Double it will be 60 and then subtract 15. How much it will be? 45 and then put a minus sign. So this is your ISA temperature at 30,000 feet. Okay, so friends, likewise you can try another examples to find the ISA temperature. Okay, now let's discuss about ISA pressure model. So in ISA pressure model, what do we learn? We should know that as the altitude increases, the pressure reduces. So let us take another example. Suppose there is a flight which is operating at 33,000 feet. 33,000 feet, where the actual temperature is suppose minus 41 degrees Celsius. Okay, suppose this is a condition. Now let's find in which ISA condition is this flight being operated. Okay, so to find out, again let's find the ISA temperature at 33,000 feet. So what will be the double of 33? 66 minus 15 equal to how much? Minus 51. So the ISA temperature at 33,000 feet is, so the ISA temperature at 30,000 feet is minus 51. How much difference is there between minus 51 and the actual temperature? That is minus 41. How much difference is there? 10. Okay, 10 is the difference. And if we compare the ISA temperature, which is minus 51 at 33,000 feet, and minus 41, which is the actual temperature at 33,000 feet, the difference is 10. Okay, now check whether the actual temperature, which is minus 41 degrees Celsius over here, is warmer or colder than the ISA temperature, which is minus 51 degrees Celsius now. So if it's colder, put a minus sign, and if it is warmer, put a plus sign here. So the ISA condition is ISA plus 10. And how much difference is there? By 10 degrees. So if we compare this and this, the actual temperature is 10 degrees ahead of the standard. Hence, hence at 33,000 feet, the flight is operating in which ISA condition? It is ISA plus 10 condition. I hope this is clear now. So now let's discuss about the ISA pressure modeling. So you should know that in ISA pressure modeling, okay, when the temperature is considered standard, that is plus 15 degrees Celsius at sea level, at this condition, with increasing altitude, the pressure reduces. Okay, so as the altitude increases, then we measure the pressure to calculate the altitude. That is, altitude measured by measuring pressure is called as pressure altitude. Note that the standard sea level pressure is 1013.25 hectopascal. If the altitude is increased by 28 feet, then there is a fall in pressure of 1 hectopascal. Note that at lower altitudes, a reduction in pressure of 1 hectopascal approximately corresponds to an altitude or pressure altitude of 28 feet, or approximately you can say 30 feet. That is, suppose you are having pressure at a certain level. Suppose this is a level having a pressure of 1013 hectopascal. Now we know that as altitude increases, pressure decreases. So how much decrease will be there? With increasing altitude, 30 feet, okay, then the pressure will drop by 1 hectopascal, that is 1012 hectopascal. Hence the conclusion, reduction in pressure by 1 hectopascal approximately corresponds to 38 feet. In books somewhere it is given as 28 feet, so you can consider 30 feet approximately for your calculations. So this is about pressure modeling. So what all things to note over here in pressure modeling? The ISA standard pressure at sea level is 1013.25 hectopascal or 29.921 inch mercury. Second thing is the altitude, whatever is measured using the pressure, is called as the pressure altitude. And third thing is a reduction of 1 hectopascal approximately corresponds to 30 feet increase in altitude. So I hope you are clear with what is International Standard Atmosphere, ISA. Then we have discussed about the temperature modeling, this one. Then we have done some calculation, how to calculate the ISA temperature at a certain altitude. And then we have discussed about the pressure modeling. So I'll come up again with a new topic in the next session. Till then, enjoy learning. Thank you.